To understand the wolf, we must first learn to look through the veil of time, back to a world that no longer exists. Before the first howl ever pierced the silence of a Pleistocene forest, there was a blueprint, a ghost in the fossil record. To find the true origin of the world's most efficient hunter, we cannot simply look at the wolf standing before us. We must descend into the deep lineage of the Canidae, a family tree etched in bone and shaped by millions of years of relentless trial and error. The story does not begin with a predator, but with a scavenger. Roughly 40 to 50 million years ago, the ancestors of all canids were small, fox-like creatures, navigating the shifting landscapes of the Eocene. They were opportunists, surviving on the fringes, possessing a generalist anatomy that allowed them to pivot between diets. But as the Earth's climate shifted, forcing forests to recede and vast, open grasslands to emerge, the rules of survival changed. Being a generalist was no longer enough. To survive the open plains, you had to be able to move. You had to be able to endure. By the Miocene epoch, we see the emergence of the Borophagini, often called the bone-crushing dogs. These were the heavyweights of the ancient canid world. They possessed massive, robust skulls designed to crack bone, occupying a niche more akin to a modern hyena than a wolf. They were powerful, yes, but they were built for brute force, not the elegant, sustained pursuit that would later define the wolf. They were the evolutionary dead end of power, a reminder that in the arms race of nature, strength without stamina is a fleeting advantage. The true revolution occurred with the rise of the Canidae, the lineage that would eventually lead to us. As the Pliocene gave way to the Pleistocene, a pivotal divergence occurred. A group of ancestral canids began to move away from the bone-crushing lifestyle and toward a specialized, cursorial, or running existence. This was the birth of the pursuit predator. Through a process of subtle, incremental refinement, their limbs grew longer, their toes more compact, and their metabolic efficiency began to skyrocket. We see the shadows of this transition in fossils like Canis etruscus, a crucial ancestor that bridged the gap between primitive canids and the true wolves of the Ice Age. These were the architects of the hunt. They were beginning to master the art of the low-energy kill, the ability to track prey over vast distances, wearing them down through sheer, unrelenting persistence rather than a single, explosive burst of energy. This was not a sudden leap, but a slow, agonizingly beautiful sculpting of biology. Every stride, every tightening of the jaw, and every refinement of the inner ear was a response to a world that was becoming increasingly competitive. The wolf was not invented, it was distilled. It was the result of millions of years of pruning away the inefficient, the slow, and the weak. The ghost of the Paleolithic is this realization. The wolf is not merely an animal. It is a living, breathing record of every successful hunt, every narrow escape, and every evolutionary gamble taken since the dawn of the canid lineage. The machine was being built, one bone at a time. But what does it actually mean to be a machine of bone and sinew? If we were to strip away the fur, the muscle, and the instinct, what would we find beneath? To understand the wolf's dominance, we must look past the aesthetics of the predator and into the cold, hard physics of its frame. The wolf is not built for the sprint of a cheetah, nor the sheer explosive power of a big cat. Instead, it is a masterpiece of biomechanical efficiency, a specialized engine designed for a singular purpose, the long-distance pursuit. The foundation of this machine begins with the vertebral column. Unlike many predators that possess a highly flexible, almost serpentine spine, the wolf's spine is a study in controlled stability. It acts as a sophisticated suspension system. As the wolf gallops, the spine undergoes a rhythmic flexion and extension, working in tandem with the limbs to maximize stride length. This is not merely movement, it is energy reclamation. With every leap, the spine and the surrounding connective tissues act like coiled springs, storing elastic energy during the descent and releasing it to propel the animal forward. This elastic recoil is the secret to their legendary stamina, allowing them to cover miles of rugged terrain while consuming significantly less metabolic fuel than a predator built for short bursts. Then we move to the limbs, where the true engineering of the cursorial specialist reveals itself. If you look closely at the wolf's leg, you will notice a remarkable evolutionary trade-off: the reduction of unnecessary weight. In the pursuit of speed and endurance, the wolf has undergone a process of distal lightening. The heavy muscle mass is concentrated close to the torso, near the hips and shoulders, where it can provide powerful leverage. As we move down the limb toward the paw, the heavy musculature gives way to long, lightweight bones and incredibly efficient, cord-like tendons. This creates a pendulum effect. By minimizing the weight at the end of the limb, the wolf reduces the moment of inertia, the energy required to swing the leg forward. This allows for a rapid, repetitive stride that can be maintained for hours without the onset of catastrophic muscle fatigue. Furthermore, the wolf's skeletal structure is optimized for digitigrade locomotion. They do not walk on their heels like humans, they walk on their toes. This elevated stance effectively adds a functional segment to the leg, lengthening the lever arm and increasing the stride without the need for more bone. Even the scapula, or shoulder blade, is not anchored to the ribcage by a rigid collarbone, as it is in humans. Instead, it is attached via a complex web of muscle and ligament. This floating shoulder provides a massive range of motion and acts as a shock absorber, dissipating the massive kinetic forces generated when a wolf's paws strike the earth at high speeds. Every joint, every ligament, and every millimeter of bone has been calibrated by the relentless pressure of the hunt. The wolf's skeleton is not a cage for its life. It is a high-performance chassis, engineered to turn the act of running into a weapon of attrition. The machine was no longer just being built, it was being perfected. But a machine, no matter how perfectly engineered its chassis, is blind and deaf without its sensors. A high-performance engine is useless if it cannot perceive the terrain ahead or the target in the distance. For the wolf, survival does not depend merely on the ability to move, but on the ability to perceive, to transform the invisible signals of the wilderness into a coherent, tactical map of reality. This is where we move from the mechanics of the body to the mastery of the senses. If the skeleton is the hardware, then the senses are the sophisticated input systems that dictate every movement of the hunt. We begin with the most profound of these inputs, the olfactory landscape. To a human, the air is a transparent void. To a wolf, the air is a dense, swirling tapestry of information. While we rely on sight to navigate our world, the wolf lives in a world of scent. Through millions of years of refinement, the wolf's olfactory bulb, the part of the brain dedicated to processing smell, has become disproportionately massive. But the true secret lies in the vomeronasal organ, or Jacobson's organ, tucked away in the roof of the mouth. This allows the wolf to perform flamen, a subtle curling of the lip that draws pheromones and chemical signals into a specialized sensory chamber. This is not just about finding food, it is about reading history. A wolf can scent a trail that is days old, detecting the microscopic skin cells and hormonal shifts left behind by a wounded elk. They can smell the fear of a prey animal through the chemical markers of cortisol released into the wind. In the dark, or through the thickest brush, the wolf isn't looking for a shape. It is tracking a chemical ghost. Yet, as the hunt enters the final, high-speed phase, scent must be supplemented by the precision of sight. While wolves do not possess the hyper-specialized color vision of many primates, they have evolved a superior nocturnal advantage, the tapetum lucidum. This is a reflective layer of tissue situated behind the retina, acting like a biological mirror. It reflects light back through the photoreceptors a second time, effectively doubling the light available to the eye. This allows a wolf to detect the slightest shimmer of movement in the moonlight, turning a pitch-black forest into a landscape of high-contrast shadows. Their eyes are not just cameras. They are light amplification devices designed to catch the silhouette of a fleeing calf against a dim horizon. But even sight and scent have limits, especially in the cacophony of a crowded herd or the howling winds of the tundra. This is where the third pillar of their sensory supremacy takes hold, the auditory sweep. The wolf's ears are highly mobile, controlled by a complex network of muscles that allow them to act as independent parabolic dishes. They can rotate their pinny to triangulate the exact origin of a sound, even if it is muffled by snow or dense canopy. More impressively, they operate within a frequency range that allows them to detect the subtle, low-frequency vibrations of heavy footsteps or the high-pitched distress calls of a yearling. This auditory precision allows the pack to coordinate not just with each other, but with the very rhythm of the environment. When scent, sight, and sound converge, the wolf achieves a state of total situational awareness. They do not merely react to the world, they anticipate it. The machine is now fully online, its sensors calibrated, its target locked. But even with the most sophisticated sensors in the natural world, a predator faces a fundamental, brutal reality. The hunt is not a constant. For every moment of high-octane pursuit, there are days, sometimes weeks, of absolute nothingness. The sensory map may be clear, and the chassis may be strong, but if the fuel runs out, the machine stalls. To survive the unpredictable rhythms of the wild, the wolf had to evolve something far more profound than mere physical strength. It had to evolve a metabolic miracle. In the world of most mammals, hunger is a crisis. When blood glucose levels drop, the body enters a state of panic, breaking down muscle tissue to find energy, leading to lethargy, cognitive decline, and eventually, death. But the wolf operates on a different biological clock. They have mastered the art of the feast and famine cycle, transforming their bodies into highly efficient biological batteries capable of storing vast amounts of energy and deploying it with surgical precision. This begins with a specialized physiological adaptation known as metabolic flexibility. When a wolf successfully brings down a large ungulate, they don't just eat, they gorge. They are capable of consuming up to 20 pounds of meat in a single sitting, a massive caloric influx that would cause systemic shock in most animals. Instead, the wolf's endocrine system orchestrates a rapid transition, diverting these nutrients into massive adipose stores and, more importantly, into the liver as glycogen. But the true genius of the wolf lies in what happens when the meat runs out. As the days of fasting stretch on, most predators would begin to cannibalize their own vital organs for fuel. The wolf, however, possesses a highly refined, glucose-sparing mechanism. As insulin levels plummet, the wolf's metabolism undergoes a profound shift, switching from carbohydrate oxidation to ketosis. Through a process of gluconeogenesis, the wolf's liver begins to convert non-carbohydrate sources, like glycerol from fat stores and specific amino acids, into the glucose required to fuel the brain. This allows the wolf to protect its hard-earned muscle mass, preserving the very fibers needed for the next high-speed chase. They are not just surviving on fat. They are chemically reconfiguring their entire internal chemistry to ensure that the engine remains primed, even when the tank is nearly empty. Furthermore, wolves exhibit a unique resistance to the systemic inflammation that typically accompanies starvation. In many species, prolonged fasting triggers a cascade of metabolic waste that damages cellular structures. The wolf's cellular pathways are optimized to manage oxidative stress, allowing them to endure the physiological toll of a lean winter without losing the cognitive sharpness required to lead a pack or coordinate a complex ambush. This metabolic resilience is the invisible backbone of their success. It is what allows a wolf to track a scent for 10 miles through a blizzard, even when its stomach is a hollow ache. It is what allows them to remain vigilant, tactical, and lethal, even when they haven't tasted blood in a week. The wolf does not merely hunt with its teeth, its eyes, or its ears. It hunts with its very cells. It is a predator that has turned the scarcity of the wild into a tactical advantage, proving that in the game of evolutionary survival, the ability to endure the void is just as important as the ability to conquer the prey. But once the metabolic engine has fueled the pursuit, and the wolf has finally closed the distance, the hunt moves from a game of endurance to a moment of absolute, violent precision. What happens in those final, frantic seconds? To bridge the gap between the chase and the kill, the wolf relies on its most ancient and specialized tool, the skull. If the metabolism is the engine, the jaw is the delivery system of lethal force. But a wolf's mouth is not merely a set of teeth. It is a highly engineered mechanical system designed to solve a specific, terrifying problem. How do you bring down an animal that is 3 times your size, covered in thick hide, and capable of shattering your bones with a single kick? The evolution of the wolf's dentition is a masterclass in functional specialization. Unlike the uniform teeth of many omnivores, the wolf possesses a dental toolkit where every tooth has a dedicated tactical role. At the front, the incisors are small but crucial, acting as precision instruments for grooming and, more importantly, for stripping meat from bone with surgical efficiency. Then, there are the canines, the primary weapons of the strike. These are not just long. They are deeply rooted into the maxilla, designed to withstand the immense lateral forces of a struggling prey animal without snapping. But the true engineering marvel lies in the carnassials. Located near the back of the jaw, these specialized premolars and molars function less like teeth and more like heavy-duty shears. Through millions of years of selective pressure, the upper fourth premolar and the lower first molar have evolved to slide past one another with terrifying accuracy. This creates a shearing action capable of slicing through thick tendons and tough hide that would stall the bite of lesser predators. However, teeth alone are nothing without the power to drive them home. This is where the physics of jaw pressure dynamics comes into play. The wolf's skull is a study in leverage. The temporalis muscle, the massive engine of the bite, is anchored to a prominent sagittal crest, a bony ridge running along the top of the skull. This crest provides a massive surface area for muscle attachment, allowing for a much higher degree of contractile force than seen in most canids. When a wolf bites, it isn't just using muscle. It is utilizing a sophisticated mechanical advantage. The jaw hinge, or the temporomandibular joint, is positioned to maximize the crushing zone. As the jaw closes, the mechanical advantage shifts, concentrating the force of the massive temporalis muscles directly onto the tips of the canines. This creates a localized pressure so intense it can puncture hide and reach vital arteries or the windpipe in a single, decisive clamp. Yet there is a hidden complexity to this force. A wolf must balance raw power with structural integrity. If the jaw were too rigid, the impact of a struggling elk could fracture the predator's own skull. Instead, the wolf's skull possesses a subtle, built-in elasticity. The sutures between the cranial bones allow for microscopic movements, acting as shock absorbers that dissipate the kinetic energy of the struggle. In the end, the bite is the final punctuation mark of the hunt. It is the moment where metabolic endurance, skeletal mechanics, and dental precision converge into a single, decisive act of survival. The wolf does not just bite to eat, it bites to conquer. But what if the most lethal weapon in the predator's arsenal wasn't a tooth, a claw, or a jaw, but a relationship? For millions of years, the lineage of the canid was defined by the solitary struggle. To be a hunter was to be an island. A lone predator survives by being fast, being quiet, and being lucky. But luck is a fickle companion, And in the unforgiving landscapes of the Pleistocene, a single mistake, a broken leg, a missed strike, a failed pursuit, meant certain death. The solitary hunter is limited by the physics of one body. One set of eyes to scan the horizon, one mouth to consume, and one strength to face the prey. Evolutionary pressure began to demand a solution to this biological ceiling. The transition from the lone stalker to the social unit was not a sudden leap, but a slow, calculated shift in the very fabric of canid behavior. It began with the realization that the cost of cooperation was lower than the cost of isolation. Imagine a world of scarcity, where the prey was not just fast, but massive. A single wolf, no matter how perfectly engineered, can rarely bring down a healthy bison or a full-grown moose without risking catastrophic injury. But a group changes the math of the hunt. This transition required a fundamental rewiring of the brain. It wasn't enough to have the physical tools, the wolf needed the cognitive architecture for social intelligence. This meant the emergence of theory of mind, the ability to predict the movements of not just the prey, but of their own kin. To hunt as a unit, a wolf must understand that if they move left, their sibling will move right. They had to learn to read the subtle intentions of others through scent, posture, and gaze. This shift introduced a new, complex biological phenomenon, the division of labor. In the solitary era, every task fell on one individual. In the dawn of the pack, roles began to emerge. We see the beginnings of what biologists call niche partitioning within a single family unit. Some individuals became the scouts, utilizing their sensory supremacy to track movement across vast distances. Others became the drivers, the high-energy pursuit specialists designed to flush prey toward an ambush. But sociality brought a new, invisible danger: internal conflict. When you move from a life of me to a life of us, you introduce the friction of competition. To prevent the pack from tearing itself apart, evolution had to craft a delicate social equilibrium. This is where we see the first traces of complex hierarchy, not as a system of tyranny, but as a mechanism for stability. By establishing a clear structure, the pack reduced the energy wasted on constant fighting, redirected that energy toward the collective goal: the kill. The most profound evidence of this transition lies in the alloparenting behavior observed in early social canids. In a solitary existence, a mother's ability to provide is limited by her own caloric intake. But in a pack, the burden of survival is distributed. The ability to share food and collectively protect the young allowed for a higher survival rate of pups, creating a feedback loop that strengthened the social bond with every passing generation. The pack was no longer just a collection of animals, it was becoming a single, distributed organism. The individual was still a masterpiece of engineering, but the pack was a masterpiece of strategy. The wolf had stopped playing a game of individual skill and had begun to play a game of collective intelligence. The era of the lone hunter was ending, the era of the tactical collective had begun. For decades, our understanding of this tactical collective was built on a foundation of a lie. If you were to walk into a classroom or watch a nature documentary from the late 20th century, you would be told a specific story: that the wolf pack is a brutal autocracy, ruled by a dominant alpha pair who maintain order through sheer, unrelenting aggression. We imagined a world of constant combat, where the strongest individual bullied the rest into submission to secure the best meat and the most fertile territory. It was a narrative of perpetual war, a survival of the fittest taken to its most violent extreme. But as we began to peer deeper into the actual biology of the pack, the myth began to crumble. When biologists first studied wolves in the wild, not in artificial, captive settings where aggression is forced by cramped quarters, they discovered something far more subtle and, frankly, far more sophisticated: The alpha is not a tyrant. In a natural, healthy pack, the hierarchy isn't a ladder of conquest. It is a map of kinship. Most wolf packs are not gangs of warriors. They are families. The individuals we once mislabeled as alphas are simply the parents. The structure is not a dictatorship, but a parental guidance system. The dominant wolves are the breeding pair, the mother and father, whose authority is derived not from the threat of violence, but from the biological necessity of rearing the next generation. The rest of the pack consists of their offspring from various years, siblings, and occasionally extended relatives. This realization fundamentally changes how we view their social intelligence. If the pack is a family, then the rules aren't enforced by a dictator to prevent rebellion. They are maintained to ensure the survival of the lineage. In a family, conflict is handled through subtle cues: a submissive posture, a lowered ear, or a specific vocalization. This is cooperative breeding, a sophisticated social strategy where the entire group shares the burden of protection and provisioning. In fact, the most successful packs are those that minimize internal friction. High levels of aggression within a pack are actually a sign of instability, a biological red flag that the social fabric is tearing. A pack that spends its energy fighting itself is a pack that cannot hunt. This leads us to a critical, less discussed mechanism of their success: social buffering. In a stable family unit, the presence of cohesive social bonds actually lowers the physiological stress levels of the individual wolves. When a pack operates as a harmonious family, their cortisol levels remain manageable, allowing them to maintain the high-focus, high-endurance state required for the long-distance pursuit. The alpha myth taught us that wolves were driven by the desire to rule. The reality teaches us they are driven by the desire to belong. Their greatness doesn't come from the strength of a single leader, but from the stability of the unit. They haven't just mastered the art of the hunt, they have mastered the art of the bond. They have turned the chaos of individual survival into the choreographed precision of a multi-generational legacy. To understand the wolf, you must stop looking for the king and start looking for the family. But if the pack is a family, how do they move as one? How does a group of individuals, spread across hundreds of acres of dense forest or frozen tundra, transform into a single, lethal organism? The answer lies not in their teeth, but in their voices. In the silence of the wilderness, sound is more than just noise. It is a data stream. For the wolf, vocalization is the invisible thread that weaves the family together, providing a continuous, real-time update on the pack's status, position, and intent. While we often associate wolves with the long, haunting melody of the howl, the true language of the hunt is far more granular, more nuanced, and infinitely more complex. To the untrained ear, a howl is a lonely cry. But to a biologist, a howl is a sophisticated piece of acoustic geometry. Recent studies in bioacoustics suggest that wolves use group howling not just for social bonding, but as a form of spatial mapping. By analyzing the pitch, duration, and frequency shifts in a howl, a wolf can determine the exact distance and direction of its kin, even through dense canopy or heavy snowfall. It is a biological GPS, allowing the pack to regroup without ever making visual contact. However, when the hunt begins, the long-distance calls give way to a much more subtle, tactical vocabulary. During the high-stakes tension of a pursuit, the wolves transition into a repertoire of short-range vocalizations: whines, growls, and barks. These are not merely expressions of emotion, they are functional commands. A specific, low-frequency growl can signal a change in direction to a flanker, or warn a sibling that the prey is about to pivot. A sharp, high-pitched whine might alert the pack to a sudden obstacle or a momentary loss of sight on the target. What is truly remarkable is the acoustic synchronization that occurs during the chase. As the pack closes in on an elk or a bison, their vocalizations become more rhythmic, almost mirroring the cadence of the pursuit itself. This creates a feedback loop of shared arousal and focus. This isn't just communication, it is a form of collective neural entrainment. The sounds allow the pack to synchronize their physiological states, ensuring that, when the finisher makes the move, the drivers are already positioned to prevent escape. Even more fascinating is the role of subvocal communication, the microsounds that occur almost beneath the threshold of human hearing. Through subtle throat vibrations and modulated breathing, wolves can convey intent and readiness. This allows them to coordinate complex, multi-stage maneuvers, such as a pincer movement, without alerting the prey. To an elk, the forest may seem silent. To the wolf, it is a deafening roar of tactical information. This ability to transmit complex, real-time data through sound is what elevates the wolf from a mere predator to a strategic mastermind. They are not just running, they are talking. They are not just chasing, they are negotiating the geometry of the kill through an invisible web of sound. In the hierarchy of the wild, strength may provide the power, but it is this shared language that provides the direction. They have mastered the most difficult feat in nature, turning a collection of separate minds into a single, communicative, and unstoppable force. But if sound is the thread that weaves the pack together, what happens when the thread begins to fray? What happens when the voices that lead the chorus grow quiet, and the hunters who set the pace can no longer keep up with the pursuit? In the brutal economy of the wild, there is a currency far more valuable than muscle mass or bite force. It is the currency of memory. We often perceive the wolf as a creature of pure instinct, a biological machine driven by the immediate demands of hunger and adrenaline. But to view them solely through the lens of instinct is to miss the most sophisticated aspect of their survival, their culture. A wolf pack is not merely a group of predators, it is a living library. And at the center of this library stand the elders. In most predator species, the alpha is defined by physical dominance. But in a long-lived wolf pack, the true leaders are often the oldest, the most weathered, and the most scarred. These are the keepers of the ecological map. While a young, vigorous wolf understands how to run, an elder understands where to run, when to wait, and most critically, what to avoid. This is where we encounter the concept of transgenerational social learning. Research into wolf demographics suggests that the survival of a pack is directly correlated to the presence of experienced adults who have survived multiple seasonal cycles. These elders hold the blueprints for survival that cannot be encoded in DNA. They remember the location of a hidden spring during a 3-year drought. They recognize the subtle shift in wind patterns that precedes a lethal blizzard. They know the specific, idiosyncratic patterns of a particular herd of elk, which individuals are prone to panic and which are prone to fatigue. This wisdom is passed down not through formal instruction, but through a process of observational apprenticeship. As pups grow into subadults, they do not simply learn to hunt by trial and error, they learn by mimicry. They watch the subtle body language of an elder as it assesses a target. They observe how an experienced wolf uses the topography of a ridgeline to mask its scent, or how it utilizes a moment of prey distraction to reposition. This is a form of non-verbal pedagogy, a silent transfer of tactical intelligence that turns a novice into a specialist. Furthermore, the elders serve as the pack's social stabilizers. In the high-stress environment of a hunt, internal conflict can be fatal. An elder wolf possesses the social intelligence to mediate disputes over carcass hierarchy or territory, using nuanced postural cues to suppress aggression before it disrupts the pack's cohesion. They maintain the social glue that allows the collective organism to function. There is a haunting beauty in this biological continuity. When an elder finally falls, the pack doesn't just lose a hunter, they lose a chapter of their history. They lose a piece of the collective intelligence that took years to compile. The success of the wolf, therefore, is not just a triumph of evolution or anatomy. It is a triumph of legacy. They have mastered the art of defying the transience of life by ensuring that the lessons of the past are carried forward into the hunts of the future. They are a species that does not just survive the present, they inherit it. But if the elders are the keepers of the library, then the pup is the blank page upon which the future of the pack is written. How does a creature born into a world of teeth and terror, essentially blind and helpless, transform into a precision instrument of the hunt? The answer lies in the delicate, often overlooked intersection of nature and nurture, a biological handoff where instinct provides the foundation, but social immersion builds the skyscraper. At birth, a wolf pup is a prisoner of its own biology. It possesses the genetic code for hunting, the neurological pathways for tracking, the instinctual drive to lunge, the primal urge to bite. This is nature, the hardwired software of a predator. But a pup born with only instinct is a dead end. In the wild, raw instinct without refined technique is merely a recipe for injury or starvation. To bridge this gap, the pup must undergo a period of intense, socialized education. This process begins long before the first chase. In the early months, the pup's world is one of sensory saturation. They are not just playing, they are conducting low-stakes simulations. When you see a litter of pups wrestling, tumbling, and nipping at one another's flanks, you are witnessing the fundamental training of the kill bite. These play sessions are critical for developing proprioception, the brain's ability to understand where the body is in space, and for fine-tuning the inhibited bite. A pup must learn exactly how much pressure to apply to a neck to subdue, but not to kill, a pack mate. This is the neurological calibration of the predator. As they transition into subadulthood, the pup moves from simulation to observation. This is where the nurture becomes sophisticated. They begin to shadow the adults, participating in what biologists call social facilitation. They don't just watch the hunt, they learn the nuances of the pre-hunt tension. They learn to read the subtle, almost imperceptible shifts in the pack's collective posture. The way a single tail flick or a slight lowering of the head signals the transition from scouting to the actual pursuit. Interestingly, research suggests that pups do not just learn how to hunt, they learn what to hunt. Through social learning, they acquire a prey preference. A pup raised in a pack that specializes in bison will develop different tactical nuances and even different physiological readiness than a pup from a pack that tracks caribou. They are learning the specific rhythms, the seasonal migrations, and the behavioral tells of their specific ecosystem. This period of apprenticeship is a high-stakes gamble. There is a window of vulnerability where a young wolf is too large to be ignored by prey, but too inexperienced to outmaneuver it. If the nurture fails, if the social structure of the pack is fractured or the elders are absent, the pup's nature will never be fully realized. They may have the teeth, but they will lack the timing. Ultimately, the pup is the vessel for the pack's survival. They are the bridge between the ancestral memory held by the elders and the unpredictable challenges of a changing landscape. Through this synergy of inherited instinct and social mastery, the pup ceases to be an individual hunter and becomes a component of the pack's collective intelligence. They do not just learn to hunt, they learn to belong to the hunt. But what happens when the very social cohesion that builds the hunter begins to fray from within? In the wild, a pack is a paradox. It is a masterpiece of cooperation, yet it is built upon a foundation of intense, often violent, competition. To the untrained eye, a skirmish between wolves looks like chaos, a flurry of snapping jaws and snarling dominance displays. But beneath the surface of this aggression lies a sophisticated mechanism of social regulation. For a wolf pack to function as a single, lethal organism, it must first solve the problem of itself. If a pack cannot manage its own internal friction, it will inevitably succumb to external pressure. A fractured pack is a dead pack. When social hierarchy collapses into constant, unresolved infighting, the collective mind we discussed earlier shatters. Energy that should be spent on scouting prey or defending territory is instead bled away in domestic strife. In the brutal economy of the wild, an ounce of wasted energy is an ounce of lost survival. This is where the true genius of wolf sociality reveals itself. Unlike many social mammals that rely on sheer, unbridled aggression to maintain order, wolves utilize a complex system of ritualized aggression. Most conflicts are not intended to maim or kill, but to communicate. Through a subtle lexicon of ear positions, tail heights, and even the specific scent of pheromones released during stress, wolves negotiate their status without the need for a lethal fight. This is a biological necessity. A wounded alpha is a liability, and a dead subordinate is a lost hunter. One of the most fascinating, less documented aspects of this stability is the role of social buffering. Studies have shown that in stable packs, the presence of a high-ranking, calm individual can actually lower the cortisol levels of subordinates during times of extreme environmental stress, such as a harsh winter or a failed hunt. The hierarchy acts as a psychological stabilizer. When the group is under pressure, the social structure provides a predictable framework that prevents panic. However, the most critical component of conflict resolution is the reconciliation phase. Much like human social structures, wolves engage in post-conflict ritual, brief moments of physical contact or relaxed posture that signal the end of a dispute. This prevents the escalation spiral, where a minor disagreement over a piece of carrion could otherwise devolve into a feud that destabilizes the entire unit. There is also the phenomenon of dispersal as a pressure valve. When internal tension becomes too great, or when the competition for resources threatens the stability of the core group, young adults will make the perilous decision to leave the pack entirely. This social pruning prevents the pack from becoming overpopulated and overstressed, ensuring that those who remain are those most capable of maintaining the social contract. In the high-stakes theater of the hunt, there is no room for resentment or distraction. When a pack closes in on a wounded elk, every wolf must be in perfect psychological alignment with the others. A single moment of hesitation caused by a lingering grudge or a lapse in coordination due to a broken hierarchy can mean the difference between a feast and a famine. To master the hunt, the wolf must first master the self, and more importantly, the group. Internal stability is not just a social luxury. It is the silent, invisible armor that protects the pack from the unforgiving reality of the outside world. If the pack is a machine, then what is its soul? To understand the wolf, one must look past the individual animal and perceive something far more haunting, a distributed intelligence that exists only in the space between them. When a pack moves through a dense forest, they do not move as a collection of separate entities, but as a single, multi-bodied organism. This is the collective mind. It is a phenomenon where the cognitive load of survival, the scanning for threats, the tracking of scents, the calculation of distance, is shared across the group. No single wolf needs to be omniscient because the pack as a whole is. This cohesion is driven by a level of non-verbal synchronization that borders on the telepathic. While we often focus on the howl, the true language of the collective mind is written in micro-movements. Research into social facilitation suggests that wolves possess a highly tuned ability to mirror the physiological states of their packmates. When one wolf detects the subtle scent of an elk, a ripple of heightened alertness passes through the group, not through a vocal command, but through a cascading chain of sensory cues. This is stigmergy in action, a mechanism where the behavior of one individual leaves a trace in the environment or the social atmosphere that triggers a specific, coordinated response in another. This synchronization extends into the very physics of the hunt. In a process known as spatial coordination, wolves demonstrate an uncanny ability to maintain optimal distances from one another without visual contact. As they surround a target, they are essentially operating on a shared mental map of the terrain. They aren't just running, they are calculating the geometry of the encirclement. A wolf on the flank doesn't need to see the wolf in the center to know exactly when to pivot. It responds to the shifting pressure of the herd and the subtle, rhythmic cues of its kin. Perhaps the most profound evidence of this collective intelligence lies in their distributed decision-making. When a pack encounters a significant obstacle, a swollen river or a particularly formidable bison, they do not act on impulse. Instead, they engage in a form of communal assessment. There is a subtle, collective weighing of risks. Through a series of low-frequency whines and postural shifts, the pack reaches a consensus. This prevents the erroneous leader problem, where a single impulsive individual might lead the group into a lethal trap. Instead, the pack moves with a unified intent, a singular will that is greater than the sum of its parts. This is not merely cooperation, it is an evolutionary leap. By distributing intelligence, the wolf overcomes the biological limitations of the individual. A single wolf is limited by its eyes, its ears, and its fatigue. But a pack has 1,000 eyes, a dozen noses, and a shared reservoir of stamina. As they converge on their prey, the individual identities of the wolves begin to blur. The alpha is no longer just a leader, and the subordinate is no longer just a follower. In the heat of the pursuit, they become limbs of a single, predatory intellect. They are a ghost in the machinery of the wild, a singular, breathing entity of teeth and bone, moving with a purpose that no solitary hunter could ever comprehend. This is the pinnacle of social evolution, the moment when the many become one, and the one becomes a god of the hunt. But even a god of the hunt must be pragmatic. Before a single muscle is flexed in pursuit, before the first stride of the chase is taken, there is a moment of profound, calculated stillness. Because in the brutal economy of the wild, a hunt is not just a test of strength. It is a high-stakes gamble where the cost of failure is starvation, and the cost of a mistake is death. The hunt does not begin with the chase, it begins with the gaze. To the untrained eye, a wolf watching a herd of elk appears to be merely waiting. But beneath that stillness, a sophisticated diagnostic process is underway. This is the phase of selection and scouting, the intellectual preamble to the physical violence. The pack is not looking for prey, they are looking for a vulnerability. They are performing a real-time biological audit of the herd. They are scanning for the biological tell. Through a combination of long-range visual tracking and scent sampling, the pack's collective intelligence begins to filter the herd. They are looking for the subtle asymmetries in movement. The slight limp of an aging bull, the lethargic gait of a malnourished calf, or the heavy, labored breathing of an animal struggling with the heat. This is an exercise in risk mitigation. To attack a healthy, prime adult is to risk a catastrophic injury, a broken jaw or a punctured lung. That could cripple an individual and, by extension, weaken the pack. The wolves are masters of cost-benefit analysis, a concept we often reserve for human economics. They are calculating the caloric expenditure of the pursuit against the likely nutritional yield of the kill. If the target is too large, the energy required to bring it down may exceed the energy provided by its meat. If the target is too fast or too alert, the probability of failure rises. The pack is searching for the sweet spot, the individual whose physical decline has made them a statistical certainty. During this scouting phase, the pack utilizes a tactic known as information gathering through proximity. They do not simply watch from a distance, they move through the landscape to intercept scent plumes. A wolf can detect the hormonal signatures of stress or illness in an animal from miles away. They are sniffing for the chemical markers of a compromised immune system or the pheromones of a predator-stressed individual. They are reading the invisible chemistry of the forest. As they scout, they are also mapping the escape topography. They aren't just assessing the prey, they are assessing the environment. They look for bottlenecks in the terrain, steep ravines that might hinder a flight response, or thickets that could provide cover for a wounded animal. They are looking for the geometry of the kill before it even happens. This is the quietest, most cerebral part of the hunt. It is a period of intense, silent observation where the pack's distributed intelligence works to strip away the herd's illusions of safety. They are peeling back the layers of the herd, identifying the weak link in the chain, and waiting for that single moment of biological failure. In the wild, there is no room for bravado. There is only the cold, hard math of survival. And once the pack has found their target, once the math confirms that the kill is viable, the stillness breaks. The calculation ends and the execution begins. If a hunt is a game of math, then the terrain is the board upon which that math is played. Once the target is selected, the pack does not simply run toward the prey in a straight line. To do so would be a tactical error of the highest order. In a direct sprint, the prey, often possessing greater explosive power and faster initial acceleration, would dictate the terms of the engagement. Instead, the wolves begin to manipulate the very shape of the earth. This is the geometry of the chase. As the pursuit ignites, the pack transitions from a group of individuals into a fluid, living net. They do not chase the animal, they chase the space around it. The primary objective is the elimination of escape vectors. To a wolf, a valley is not just a landscape feature, it is a funnel. A ridge is not just a mountain, it is a wall. By utilizing a technique known as encirclement positioning, the pack members spread out, instinctively seeking to occupy the high ground or the flanking positions that limit the prey's lateral movement. They are looking for topographic bottlenecks, narrow passes, dense thickets, or steep embankments, where the prey's speed is neutralized by the physical constraints of the land. There is a sophisticated, almost subconscious, understanding of line-of-sight occlusion at play here. A clever wolf will use a bend in a river or a dense stand of timber to break the visual connection between the prey and the rest of the pack. This creates a psychological, blind spot. When the prey loses sight of their pursuers, they may momentarily relax their vigilance or make a panicked, predictable turn, a turn that the wolves have already anticipated by positioning themselves in a pincer movement. But the geometry goes deeper than mere positioning. It involves the manipulation of momentum. In many hunts, wolves will intentionally drive prey toward energy-sapping terrain. They might steer a deer toward soft, marshy ground where the ungulate's heavy hooves sink and struggle, or toward a steep, rocky incline where the prey's center of gravity becomes unstable. By forcing the prey to fight the terrain as much as the predator, the wolves are effectively taxing the prey's metabolic reserves before the physical contact even occurs. This is where the distributed intelligence of the pack becomes truly terrifying. While one or two drivers push the prey forward, others act as interceptors, moving through the shadows of the landscape to cut off the most likely escape routes. They are playing a high-speed game of chess, where every hill, every thicket, and every creek bed is a piece being moved to restrict the opponent's options. They are also masters of the gradient advantage. By maintaining the high ground during a pursuit, wolves can use gravity to assist their descent, allowing them to maintain high speeds with lower caloric expenditure than the prey, which must fight against the incline. This is the physiological exploitation of the landscape. The geometry of the chase is designed to turn the world into a trap. The goal is to shrink the prey's universe until the horizon disappears, until the paths of flight are severed, and until the animal realizes, with a sudden, crushing clarity, that every direction it turns has already been claimed. The landscape is no longer a refuge. It has been transformed into a cage. The math has been solved. The geometry is closed. And as the prey is funneled into the final, inescapable corner, the chase shifts from the strategic to the visceral. The distance closes, the terrain vanishes, and the hunt moves into its most violent, decisive phase. But as the cage closes, a profound biological tension begins to emerge. A battle between two fundamentally different ways of moving through the world. If the geometry of the chase is the mind of the hunt, then the physiological conflict is its soul. To the untrained eye, a hunt looks like a frantic sprint. But if we look closer, at the cellular level, we see that the wolf is not playing a game of speed. It is playing a game of time. In the natural world, there is a fundamental trade-off between power and persistence. Most of the wolf's prey, the elk, the moose, the deer, are built for explosiveness. They are the sprinters of the forest. Their muscle fibers are dominated by type II fast-twitch fibers, designed for massive, anaerobic bursts of speed. When a deer senses danger, it can achieve a staggering acceleration, a sudden violent release of kinetic energy that can leave a predator in the dust within seconds. But this power comes at a heavy metabolic cost. These explosive bursts rely on glycolysis, a rapid, inefficient way of creating energy that produces lactic acid as a byproduct. For an ungulate, that lactic acid is a ticking time bomb. It burns in the muscles, creates excruciating pain, and eventually leads to metabolic acidosis, forcing the animal to slow down or collapse. The wolf, however, has evolved to be the ultimate slow-burn predator. While the prey is fueled by the volatile fire of anaerobic sprinting, the wolf operates on the steady, relentless glow of aerobic endurance. Their bodies are masterfully engineered for oxidative metabolism. Their skeletal muscles possess a high density of type I slotwich fibers, packed with mitochondria, the microscopic power plants of the cell. These mitochondria are incredibly efficient at using oxygen to turn fat and glycogen into a steady stream of ATP, the energy currency of life. This is the science of the steady state. A wolf can maintain a trot or a rhythmic gallop for miles, barely breaking its metabolic stride, while its prey is forced into a cycle of frantic, energy-depleting sprints. This is not just a physical difference, it is a thermodynamic strategy. The wolf is essentially outlasting the prey's ability to regulate its own internal chemistry. As the chase enters its second, third, or even fourth hour, a phenomenon known as metabolic decoupling occurs. The prey's heart rate is redlining, its core temperature is spiking toward dangerous levels, and its muscles are screaming under the weight of accumulated lactate. It is running out of fuel in the most literal sense. Meanwhile, the wolf, through efficient thermoregulation and a highly developed cardiovascular system, maintains a relatively stable internal environment. They are moving through a landscape of exhaustion that they themselves are creating. In the wild, this is often referred to as cursorial hunting, the pursuit of prey through sustained, rhythmic movement. It is a grueling, low-intensity attrition. The wolf does not need to be faster than the deer. It only needs to be more consistent. It waits for the moment when the prey's explosive capacity is spent, when the fast-twitch muscles fail, and when the sprinter becomes a walker. The hunt, therefore, is a slow-motion collapse. It is the systematic stripping away of the prey's kinetic potential, one heartbeat at a time. The wolf isn't just chasing an animal, it is chasing the inevitable moment when biology itself turns against the prey. The sprint ends, the endurance begins, and the slow burn consumes everything in its path. But what if the prey's greatest defense, the strength of the herd, is actually its greatest vulnerability? If the physiological hunt is a battle of thermodynamics, then the mental hunt is a battle of perception. To understand the wolf, you must understand that they do not merely hunt animals, they hunt the collective psyche of the group. For a herd of elk or bison, survival is predicated on a single, ancient rule: safety in numbers. This is the dilution effect, the mathematical hope that by being part of a massive, moving wall of flesh, the statistical probability of any one individual being targeted is minimized. But a wolf pack knows how to shatter that math. They begin with what biologists call the shadow phase. They do not charge, they haunt. By appearing on the periphery of a herd, the pack initiates a state of chronic hypervigilance. This is not a passive observation, it is a calculated psychological siege. Through subtle movements and strategic positioning, the wolves force the herd into a state of allostatic load, a physiological wear and tear caused by constant, low-level stress. The herd's cortisol levels spike, their heart rates climb, and their ability to make rational, collective decisions begins to erode. The goal of this psychological warfare is to induce social fragmentation. A healthy herd moves as a singular, cohesive unit, a rhythmic tide of instinct. The wolves seek to disrupt this cohesion. They use targeted harassment, focusing their attention not on the strongest members, but on the fringes. They look for the spatial outliers, the calf that has drifted a few feet too far, the elder whose reaction time has lagged by a fraction of a second, or the individual that shows signs of sensory distraction. This is where the wolf utilizes a phenomenon known as predatory contagion. By repeatedly nipping at the edges and then vanishing, the wolves create a sense of unpredictable chaos. They break the herd's group synchrony. In a state of panic, the herd's communication breaks down. The collective intelligence that once allowed them to sense a threat in unison is replaced by a frantic, individualistic scramble for survival. As the herd's internal order collapses, the scapegoat effect takes hold. In the chaos of a panicked stampede, individuals often collide, trip, or become separated from the protective center. The wolves are waiting for this exact moment of cognitive dissonance, the moment when the herd ceases to be a single organism and becomes a collection of terrified, isolated individuals. They are looking for the break point, the precise moment when the psychological pressure of the pursuit outweighs the herd's instinct to stay together. Once that social bond is severed, the prey is no longer part of a protected collective. It is an individual in crisis. By the time the physical chase truly intensifies, the mental battle has already been won. The wolf hasn't just found a weak animal, they have systematically dismantled the very social structure that made the animal strong. They have turned the herd's greatest asset, their unity, into a source of panic and confusion. The hunt is no longer just a pursuit of flesh. It is the exploitation of fear, a masterful manipulation of the instinct to belong, used to isolate the one soul that can no longer run with the rest. But once the herd's unity is shattered, a new, more disciplined order takes its place, the order of the pack. If the prey's defense is chaos, the wolf's offense is a highly choreographed symphony of movement. This is not a frantic scramble of predators. It is a sophisticated division of labor that mirrors the tactical maneuvers of highly trained military units. To the untrained eye, it looks like a riot of fur and teeth, but beneath the surface lies the coordination dance, a series of specialized roles that transform a group of individuals into a single, lethal machine. As the target is isolated, the first role engages, the driver. The driver's objective is not to kill, but to direct. Using high-speed bursts of energy, these wolves act as the psychological architects of the chase. They do not approach the prey head-on. Instead, they use lateral movements to steer the target. They are the shepherds of the hunt, utilizing directional harassment to funnel the prey toward specific terrain, a narrow ravine, a muddy marsh, or a dense thicket where the prey's speed is compromised. By controlling the geometry of the chase, the driver ensures that the target is not just running, but running exactly where the pack needs it to be. While the driver dictates the path, the flankers execute the containment. Flankers are the masters of spatial positioning. As the prey attempts to veer away from the driver's pressure, the flankers emerge from the periphery, cutting off escape routes with surgical precision. This is a feat of incredible cognitive mapping. A flanker must constantly calculate the prey's trajectory, adjusting their own gait and angle to maintain a closing gap without triggering a premature flight response that might lead the prey into safety. They occupy the interstitial spaces, the gaps between the herd and the horizon, effectively creating a moving perimeter. Through this encirclement, they compress the prey's world, shrinking their field of movement until the only direction left is forward, straight into the trap. Then there are the finishers. The finishers are the specialists of the terminal phase. They are often the most experienced members of the pack, possessing the highest level of bite force efficiency. While the drivers and flankers manage the macro movements of the chase, the finishers focus on the micromechanics of the kill. They do not waste energy on the chase. They wait for the moment of physiological exhaustion. As the prey's aerobic capacity hits its limit, a state known as metabolic collapse, the finishers strike. They do not aim for the center of mass, which is often protected by thick muscle or heavy bone. Instead, they utilize targeted trauma, focusing their strikes on highly vulnerable anatomical points: the throat to induce asphyxiation, or the hindquarters to sever the tendons and immobilize the animal. This is the culmination of the dance, a transition from the kinetic energy of the pursuit to the surgical precision of the strike. This specialization is more than just instinct. It is an evolutionary masterstroke. By distributing the energetic costs of the hunt, the driver providing the direction, the flanker providing the containment, and the finisher providing the lethality, the pack minimizes the risk of injury to its most valuable members. In the coordination dance, the wolf has achieved something rare in the animal kingdom: the ability to transcend the limitations of the individual, turning the hunt into a collective masterpiece of biological engineering. But even the most perfectly choreographed masterpiece can end in disaster. What happens when the symphony breaks? What happens when the single, lethal machine of the pack suddenly fractures into a collection of desperate, hungry individuals? In the wild, failure is not merely an inconvenience, it is a biological catastrophe. A failed hunt represents a massive energetic deficit, a period where the pack has expended thousands of calories in pursuit, only to receive zero caloric return. For a wolf, this is a move toward the brink of starvation. Yet, it is within these moments of profound failure that the true genius of the wolf is revealed. They do not just recover, they recalibrate. Consider a scenario where a pack targets a large bull elk. The drivers execute their roles, the flankers close the perimeter, and the finishers move in. But perhaps the elk, fueled by a final, desperate surge of adrenaline, manages to break the encirclement. Perhaps a flanker miscalculates the terrain, or a finisher strikes a heavy rib instead of a soft throat, resulting in a broken tooth or a lacerated limb. The prey escapes. The pack is left with nothing but the heavy, rhythmic breathing of exhaustion and the bitter taste of defeat. In many predator species, such a failure would trigger a breakdown in social cohesion, infighting, chaos, or a retreat into solitary scavenging. But wolves possess a rare cognitive trait: socially mediated learning. Following a failed hunt, the pack enters a period of subtle, high-stakes assessment. This is not a conscious debate, but a neurobiological process of error correction. Through subtle changes in body language, postural shifts, and vocalizations, the pack audits the failure. Was the prey too fast? Was the terrain too advantageous for the target? Did the coordination break down because of a lack of spacing between the flankers? Recent studies in canine cognitive ethology suggest that wolves utilize a form of observational error correction. Younger, less experienced wolves watch the reactions of the elders. If a lead female shows signs of heightened agitation or a specific corrective posture after a missed strike, the subordinates internalize that failure as a tactical data point. They are effectively updating their behavioral algorithms. This adaptation often manifests in the very next hunt. If a pack lost an elk due to a muddy ravine, the next time they encounter similar terrain, the geometry of the chase will change. They may shift from a high-speed pursuit to a more patient, low-energy stalking method to avoid the slip risk of the mud. If the failure was due to a finisher's inaccuracy, the pack may adjust its social spacing, allowing more time for the prey to reach a state of true metabolic collapse before the final engagement. This is the Red Queen effect in action, but applied internally. As the prey evolves better defenses, the wolf doesn't just evolve better teeth. It evolves a better way to process its own mistakes. Failure, therefore, is not the end of the hunt. It is the most brutal, most effective classroom in the natural world. Through the crucible of starvation and the sting of defeat, the pack refines its dance, ensuring that the next time the symphony begins, it is even more lethal than the last. But if the wolf is the architect of the hunt, then the prey is the architect of the escape. In the grand theater of evolution, no predator can hold the stage indefinitely without the audience fighting back. This is the biological reality of the Red Queen hypothesis. To stay in the same place, you must run as fast as you can. As the wolf refined its social intelligence and its metabolic endurance, it exerted a relentless, invisible pressure on the species it hunted. This pressure didn't just kill the weak. It acted as a selective sieve, filtering out every trait that made an ungulate, a deer, an elk, or a moose vulnerable. What we see today in the anatomy of a deer is not a finished product, but a living record of 1,000,000 narrow escapes. The first line of defense is the explosive twitch. While the wolf is a master of the slow burn, the long-distance aerobic pursuit, the ungulate has evolved to counter this with extreme anaerobic capacity. Deer and elk possess a high density of fast-twitch muscle fibers, designed for sudden, violent bursts of kinetic energy. This is a biological countermove. When a wolf closes the distance, the prey doesn't try to outrun the wolf for 10 miles. It tries to out-accelerate the wolf for 10 seconds. This sudden surge of speed is designed to break the wolf's visual lock and disrupt the geometry of the chase, forcing the pack to reset their entire tactical formation. But speed is useless if you cannot navigate the chaos of the hunt. This has driven an evolution in sensory perception and spatial awareness. Ungulates have developed a specialized peripheral vision, an almost panoramic field of view that allows them to detect the slightest shift in the landscape of fear. They are not just looking for a wolf, they are looking for the absence of normalcy. They sense the subtle disruption in the wind, the unnatural stillness of a thicket, or the micro-expressions of a herd mate. Perhaps most fascinating is the evolution of vigilance architecture. In many ungulate species, we see the development of complex social signaling. When a single elk detects a predator, it doesn't just run, it communicates. Through specific alarm vocalizations, or stotting, a high-stepping, rhythmic jump seen in many antelope and deer species, the prey provides a dual-purpose signal. It warns the herd, but more importantly, it serves as an honest signal to the predator. It tells the wolf, "I have seen you, I am healthy, I am prepared, do not waste your energy on me." This creates a high-stakes psychological stalemate. The wolf must decide if the caloric reward of the hunt is worth the massive energetic expenditure of chasing a highly vigilant, highly explosive target. Even the skeletal structure has been reshaped by this conflict. The ungulate limb is a marvel of lightweight efficiency, with elongated metatarsals that act as biological springs, allowing for maximum stride length with minimal muscular effort. This is the direct evolutionary response to the wolf's endurance. The prey has become a specialist in evasive geometry, using zigzagging patterns to exploit the wolf's momentum, turning the predator's own speed against it. The hunt, therefore, is not a one-sided slaughter. It is a continuous, high-speed conversation between two specialized machines, each constantly rewriting its own code to survive the other. As the wolf evolves to close the gap, the ungulate evolves to widen it. But what happens when the prey stops running and starts growing? If the ungulate's response to the wolf was to become a master of evasion, the wolf's response was to become a master of scale. There is a threshold in nature where speed no longer guarantees survival, where the only remaining defense is sheer, overwhelming mass. This is the genesis of the size escalation. For millions of years, the evolutionary dialogue was focused on the sprint. But as wolves mastered the slow burn of endurance, a new biological opportunity emerged: the ability to target the giants. To move from hunting the deer to hunting the bison, the mammoth, or the giant elk, the wolf had to undergo a fundamental structural revolution. It wasn't enough to be fast, they had to become heavy-duty. This transition required a radical recalibration of the wolf's mechanical blueprint. To take down megafauna, the wolf had to solve the problem of impact force. When a 300-pound wolf lunges at a 2,000-pound bison, the physics are unforgiving. Evolution responded by thickening the cortical bone, the dense outer layer of the skeleton, to prevent fractures during the violent collisions of the hunt. The limbs, once optimized solely for a lightweight, rhythmic stride, had to gain the muscular density required to anchor a body that was wrestling with a moving mountain. But the most profound change occurred in the kill mechanism itself. In smaller prey, a shallow puncture wound might suffice. Against megafauna, a shallow wound is merely an annoyance. It is a biological insult that invites a lethal counterattack. To bridge this gap, the wolf's dentition underwent a specialized transformation. We see the refinement of the carnassial teeth, the blade-like premolars and molars that act like biological shears. These teeth evolved not just for slicing meat, but for shearing through the incredibly tough, fibrous hide and thick subcutaneous fat layers of Pleistocene giants. Furthermore, the wolf had to master the art of targeted trauma. You cannot kill a mammoth by simply biting it. Success required a sophisticated understanding of anatomy, specifically the ability to locate and exploit the soft points, the throat, the belly, or the femoral arteries. This shifted the hunt from a test of pure stamina to a high-stakes surgical operation. A pack of wolves tackling a megafauna target must operate with a level of coordinated precision that borders on the mathematical. One wolf might act as a stabilizer, latching onto a hind leg to impede movement, while another performs the vital strike. This escalation also drove a shift in social complexity. Hunting megafauna is an all-or-nothing gamble. A failed hunt against a large target doesn't just mean an empty stomach, it can mean a broken bone or a fatal injury. This increased the cost of failure, which in turn necessitated larger, more disciplined packs. The social hierarchy became a tactical necessity, a way to distribute the risk and ensure that the caloric windfall of a massive kill could sustain the entire group through the inevitable period of recovery. The size escalation was, in essence, the wolf's decision to stop playing the game of shadows and start playing the game of titans. It was a move from the periphery of the ecosystem to its very center, transforming the wolf from a mere scavenger of the edges into the primary architect of the prehistoric landscape. But if the size escalation was a battle of titans, how does a predator survive when the very ground beneath its feet transforms from a lush playground into a frozen, unforgiving wasteland? Nature does not offer a static battlefield. The wolf's greatest evolutionary strength is not just its physical prowess, but its cognitive plasticity, the ability to rewrite its tactical manual as the seasons turn. As the lush, high-density forests of summer give way to the stark, skeletal landscapes of the winter tundra, the wolf faces a fundamental shift in the physics of the hunt. In the summer, the forest is a labyrinth of vertical complexity. Dense foliage, thick underbrush, and uneven terrain provide infinite opportunities for concealment. Here, the hunt is a game of shadows and sudden, explosive bursts of movement. The pack relies on ambush-style endurance, using the cover of the timber to close the distance before the prey's heightened olfactory senses can trigger an escape. In this green world, the wolf is a ghost, utilizing the broken geometry of the trees to mask its approach. But as the snow descends, the landscape undergoes a radical simplification. The forest's complexity is buried under a white shroud, and the landscape of fear is stripped bare. In the winter tundra, there is nowhere to hide. The visual field expands, turning the hunt into a high-stakes game of long-distance detection and thermal tracking. This is where the wolf's metabolic and sensory adaptations become their primary weapons, while the ungulates, the elk, the deer, the moose, are struggling with the caloric deficit of winter. The wolf enters a state of physiological readiness. They become masters of thermal searching. A wolf can detect the heat signature of a large mammal through layers of snow and frozen air, a capability that turns the winter's emptiness into a map of potential targets. The tactics, too, must evolve. In the summer, the pack might circle and drive prey toward a thicket. In the winter, the strategy shifts to snow-depth manipulation. Wolves have evolved a specialized paw structure, large, furred, and spreading under weight, that acts like natural snowshoes. This gives them a mechanical advantage over their prey. An elk, burdened by heavy, cloven hooves, will sink deep into the drifts, its movement becoming labored and rhythmic. The wolf, however, stays on the surface, dancing across the crust. The hunt ceases to be a sprint and becomes an exercise in mechanical attrition. They don't just outrun the prey, they outfloat it. Furthermore, the winter hunt changes the very definition of a target. In summer, wolves select for weakness or youth. In the depths of winter, they select for exhaustion. They engage in what biologists call predatory tracking, following a herd for miles, not necessarily to strike immediately, but to exert a constant psychological pressure. This relentless pursuit forces the prey to burn through their precious fat reserves, effectively pre-digesting the kill before the first bite is even taken. The seasonal shift is more than a change in weather. It is a total recalibration of the predatory engine. From the tactical complexity of the summer thicket to the endurance-based attrition of the winter tundra, the wolf proves that it is not merely a creature of instinct, but a creature of profound environmental intelligence. They do not just survive the change in seasons, they weaponize it. But what if the most profound impact of a predator isn't measured in the blood it spills, but in the invisible architecture of dread it constructs? We often think of a hunt as a physical event, a chase, a strike, a kill. But for the animals living in the shadow of the wolf, the hunt is a constant, pervasive presence that exists long before a single paw hits the ground. Biologists call this the landscape of fear. It is a psychological map, drawn in the minds of every herbivore, where certain valleys, riverbanks, and dense thickets are marked not by their forage, but by their danger. The wolf does not merely consume calories, it consumes time and energy. When a wolf pack enters a territory, the very geometry of how prey move is rewritten. Consider the elk or the deer. In a world without wolves, these animals are optimal foragers. They spend their days in the most nutrient-dense areas, lush riparian zones, soft river valleys, and low-lying meadows where the grass is sweetest and easiest to digest. They prioritize caloric gain above all else. But the presence of the wolf introduces a devastating variable: the cost of being caught. Under the influence of the landscape of fear, the optimal choice changes. An elk may stand in a meadow of high-quality willow, but if that meadow offers no escape routes or leaves the animal exposed to a long-range visual approach, the elk will choose to starve slightly rather than risk the kill. They move to the suboptimal terrain, steeper slopes, thicker brush, or higher elevations. These areas are harder to navigate and the food is scarcer, but they provide the tactical advantage of sightlines and cover. This creates a phenomenon known as non-consumptive effects. The wolf is effectively hunting the prey through sheer psychological pressure, forcing them to burn more calories, navigating difficult terrain, and constantly scanning the horizon. This is a form of metabolic warfare. By dictating where an animal can safely eat, the wolf regulates the energy budgets of entire populations. The implications of this reach far beyond the individual animal. This is where we see the subtle, ghost-like hand of the wolf shaping the very earth. In areas where wolves have been reintroduced, such as the iconic corridors of Yellowstone, we see the trophic cascade in action. Because the elk are too afraid to linger in the river valleys, the willow and aspen groves are allowed to recover. These recovering plants provide habitat for songbirds and materials for beavers. The beavers, in turn, build dams that alter the hydrology of the entire ecosystem, creating wetlands that support fish, amphibians, and insects. The wolf's presence acts as a regulatory pulse. It prevents any single species from overgrazing a landscape into exhaustion. By creating a landscape of fear, the wolf enforces a spatial distribution of life. It ensures that no single patch of earth is stripped bare, because the cost of staying too long in one place becomes too high. The wolf is not just a killer, it is an architect. It doesn't just remove individuals from a herd, it reshapes the movement, the nutrition, and the very survival strategies of every living thing in its wake. The hunt is not just a moment of violence, it is a silent, shifting boundary that defines the limits of life itself. But in this architecture of dread, the wolf does not reign alone. If the wolf is the architect of the landscape, it is also a central figure in a much darker, more complex social economy, the economy of the carcass. To understand the wolf's mastery, we must look beyond the chase and into the shadow cast by the kill, a shadow where the lines between hunter, competitor, and scavenger blur into a violent dance of opportunism. In the wild, a kill is not merely a meal. It is a high-stakes epicenter of conflict. When a wolf pack successfully brings down a large ungulate, they have essentially created a concentrated burst of energy in a landscape where calories are often scarce. This sudden abundance acts as a biological siren, a chemical signal traveling on the wind that announces a windfall to every other predator within miles. This brings us to the wolf's most intimate and volatile relationship, the one with the scavenger. We often categorize animals into neat boxes. Wolves are predators, bears are omnivores, eagles are scavengers. But in the reality of the wilderness, these roles are fluid and fiercely contested. The wolf exists in a state of constant interference competition. They are not just competing for the prey itself, but for the right to access the remains. Consider the grizzly bear. While a wolf pack possesses the tactical advantage of numbers and the ability to execute a kill, a single mature grizzly possesses a level of raw, kinetic power that can render a pack's social structure irrelevant. This creates a fascinating biological tension. Wolves must balance the caloric necessity of eating as much as possible with the extreme metabolic cost of defending a carcass against a much larger opponent. In many ecosystems, wolves have evolved a stealth-and-speed strategy for scavenging, consuming the most nutrient-dense organs and marrow as quickly as possible before the larger, more formidable competitors arrive. But the relationship is not always one of direct confrontation. There is a more subtle, symbiotic tension at play. Many scavengers, such as ravens and wolverines, have evolved to be kleptoparasites, specialists in stealing food from others. The raven, for instance, is more than just a bird circling overhead. It is a highly intelligent observer that can read the subtle cues of a wolf pack's behavior. A raven may follow a pack for miles, waiting for the exact moment the wolves reach a state of post-kill satiety or distraction, only to swoop in and snatch away the scraps. Even more remarkable is the relationship with the wolverine. These small, powerful carnivores are the ultimate opportunists, capable of entering a fight with much larger animals to claim a frozen carcass. This creates a complex hierarchy of resource partitioning. To avoid constant, energy-depleting conflict, different species have evolved to utilize the kill at different stages. The wolves take the heavy lifting, the bears take the bulk. The wolverines take the frozen remnants, and the avian scavengers take the fine details. This is the shadow side of the apex predator's success. The more efficient the wolf becomes at hunting, the more it fuels a secondary ecosystem of competition. The wolf's kill is the heartbeat of a much larger, more chaotic engine of survival, a cycle where the master hunter must constantly defend its prize against the very creatures that thrive on its success. But if the scavengers are the vultures of this violent economy, we must ask, what happens to the land when the economy itself collapses? We often view the act of killing as a disruption, a momentary fracture in the peace of the wilderness. But in the grand, sweeping clockwork of evolution, the kill is not a disruption. It is a regulation. It is the vital mechanism that prevents the entire system from spiraling into exhaustion. This is the phenomenon known as the trophic cascade, and it reveals a truth that is as uncomfortable as it is profound. For a landscape to flourish, it must periodically bleed. To understand this, we have to look past the predator and the prey and look at the very soil beneath their feet. When an apex predator like the wolf is removed from an ecosystem, the result is not a peaceful paradise of abundant herbivores. It is a biological catastrophe. Without the wolf to act as a check, herbivore populations, such as elk, deer, or moose, do not simply grow, they explode. They move from being inhabitants of the landscape to being its conquerors. These unchecked herds undergo a process of hyperconsumption. They linger in the valleys, they graze the riparian zones of riverbanks until the willow and aspen are nothing but stubs, and they strip the forest floor bare. This is overgrazing on a geological scale. When the vegetation vanishes, the very architecture of the ecosystem begins to crumble. Without roots to hold the earth, riverbanks erode, water temperatures rise, and the nesting grounds for birds and the habitats for beavers vanish. The landscape becomes a desert of its own making. This is where the landscape of fear, a concept pioneered by ecologists like Robertet, becomes essential. The wolf's presence does more than just reduce numbers, it dictates movement. The mere possibility of a hunt forces prey to remain vigilant. They cannot linger in the open for hours. They must move, they must hide, and they must avoid the most vulnerable corridors of the forest. This forced mobility is the secret ingredient of a healthy ecosystem. It creates refugia, pockets of untouched vegetation where plants can grow, seeds can drop, and life can take hold. By killing, the wolf inadvertently protects the plant life, which in turn stabilizes the soil, which then provides the foundation for insects, birds, and small mammals. This is the cascade. A single kill in a high-altitude meadow can, through a chain reaction of biological consequences, determine the flow of a river miles downstream. There is a scientific nuance here that is often overlooked: the nutrient subsidy. When a wolf kills, it doesn't just move energy from a deer to a pack, it redistributes it across the entire map. The remains of a carcass, the bone marrow, the spilled viscera, the nitrogen-rich waste, act as a localized fertilizer. These hotspots of nutrients create bursts of intense plant growth in the following season, creating microhabitats that would otherwise not exist. The kill, therefore, is not an end, but a redistribution. It is the mechanism by which energy is recycled from the bodies of the mobile to the stillness of the earth. The wolf is not merely a taker of life. It is the gardener of the wild, using the blade of the hunt to prune the excesses of the world, ensuring that the cycle of growth never becomes a cycle of decay. But what happens when the gardener meets a rival who also wields the blade? For millions of years, the wolf was the undisputed master of this biological redistribution. But as the Pleistocene gave way to the Holocene, a new player entered the arena, not with claws or specialized dentition, but with a tool that fundamentally altered the physics of the hunt, the projectile. As early humans began to master stone, wood, and fire, they didn't just enter the ecosystem, they collided with it. This was not a meeting of two different worlds, but a violent convergence of two nearly identical niches. We often think of humans as being above the food chain, but in the eyes of the Paleolithic landscape, early humans were simply another high-level carnivore. And like the wolf, we were driven by the same relentless biological imperative: the need to secure high-density protein to fuel our rapidly expanding, energy-expensive brains. This created a direct, zero-sum competition. The wolf and the human were hunting the exact same targets, the same migratory herds of reindeer, bison, and horse. Every elk brought down by a human spear was a caloric loss for a wolf pack. Every bison carcass claimed by a human settlement was a meal stolen from the jaws of the wild. We were no longer just observers of the hunt. We were competitors in a high-stakes game of caloric acquisition. The tension between us was fueled by a fascinating biological phenomenon known as niche overlap. In ecology, when two species compete for the same limited resources, the pressure is immense. This competition forced both species into an evolutionary arms race of intelligence and strategy. The wolf refined its social coordination and endurance-based pursuit, while humans refined their ability to predict movement, create tools, and communicate complex plans. But there is a darker, more subtle layer to this encounter. While we competed for the same prey, we also competed for the same space. As human populations began to form more permanent seasonal camps, we effectively claimed the most fertile hunting grounds. This forced wolf packs into the margins, the steeper, more rugged, and less productive terrains. This spatial competition likely triggered a shift in wolf behavior, pushing them toward the edges of human influence, a tension that would define our relationship for millennia. However, this era of pure competition contained the seeds of a radical biological anomaly. While most competing species moved toward total exclusion, humans and wolves did something unprecedented. We began to observe one another. We saw the wolf's utility. We saw the tactical brilliance of the pack. We saw a fellow hunter that understood the language of the wild. In the shadows of these competitive skirmishes, a strange, quiet observation was taking place. We were watching the master of the hunt, and in doing so, we were beginning to see a reflection of ourselves. The collision of our niches, the struggle for the same meat and the same territory, was creating a friction that would eventually spark the greatest biological divergence in history. The competitor was about to become something else entirely. The predator was about to become the partner. What if the greatest alliance in history was born not from friendship, but from a mutual, calculated exploitation of survival? As the friction between human and wolf intensified, a biological anomaly began to flicker in the periphery of the Paleolithic landscape. It did not start with a hand reaching out in peace, but with a shared interest in the scraps of a kill. This is the era of the self-domestication hypothesis, a theory suggesting that the split didn't begin with human intervention, but with the wolves themselves making a radical, evolutionary gamble. Imagine a subset of wolves, the bold ones. In the high-stakes world of the pack, most wolves avoid the terrifying presence of humans. But a few, perhaps driven by a mutation in their neurochemistry, possessed a slightly lower threshold for fear. These were the scavengers of the periphery. They learned that the scent of human smoke often preceded the scent of calorie-rich refuse. By lingering on the edges of our camps, these wolves were engaging in a dangerous dance, trading the prestige of the apex predator for the reliable, low-risk energy of human leftovers. This was the first step in a profound neurological restructuring. To live alongside us, these wolves had to undergo a process of social buffering. They had to learn to read the subtle, nonverbal cues of a species that didn't howl or growl, but gestured and spoke. Through this proximity, a feedback loop was established. We began to favor the less aggressive, more docile wolves, effectively performing a primitive form of artificial selection. Over generations, this pressure began to reshape their very biology. The divergence was not merely behavioral, it was morphological. As these proto-dogs moved away from the wolf's life of extreme endurance and high-intensity combat, their bodies began to drift. We see this in the domestication syndrome, a suite of physical changes that occur when a species undergoes rapid selection for reduced fear. Their ears became floppier, their snouts shorter, and their coats more varied. Most significantly, their digestive systems began to adapt. While the wolf remains a strict carnivore, optimized for the heavy protein and fat of a fresh kill, the early dog began to develop the ability to digest starches, a direct result of living on the grain-heavy scraps of human settlements. But the most profound split was in the brain. The wolf's intelligence is a weapon honed for the lethal coordination of the hunt. The dog's intelligence, however, evolved into a specialized form of social cognition. They developed a unique ability to process the gaze of a human, a cognitive skill that even our closest primate relatives lack. They became masters of the human emotional landscape, capable of sensing our cortisol levels and understanding our intent. This was the Great Divergence. One lineage stayed in the shadows, refining the brutal, efficient mechanics of the wild hunter, perfecting the art of the kill to survive the unforgiving Holocene. The other lineage stepped into the light, trading the autonomy of the predator for the security of the hearth. The wolf remained the master of the landscape, but the dog became the master of the human. The hunter and the companion had split, leaving behind a biological rift that would forever change the trajectory of both species. But what happens when the companion becomes the enemy of the original? As the domestic dog moved into our homes, the wild wolf was increasingly cast as the shadow in the doorway, a relic of a dangerous, unmanaged past. For millennia, the wolf had been a silent architect of the ecosystem, but as human civilization transitioned from scattered settlements to expansive, industrial empires, the wolf was no longer viewed as a biological necessity. It was redefined as a biological threat. The era of eradication was not a series of accidental encounters. It was a calculated, global campaign of biological erasure. This was the systematic attempt to delete a species from the face of the earth. By the 19th and early 20th centuries, the philosophy of progress demanded the total subjugation of the wild. To the expanding frontiers of the Americas, Europe, and Asia, the wolf was the ultimate obstacle to the two pillars of modern wealth, livestock and land. The predator was seen as a thief, a chaotic element in an increasingly ordered world. Governments didn't just tolerate hunting, they subsidized it. In the United States, the Bureau of Biological Survey, the precursor to the Fish and Wildlife Service, was, ironically, tasked with the systematic destruction of the very species it now studied. They deployed bounties, trained specialized wolf squads, and utilized everything from strychnine poisoning to high-powered rifles. But the erasure went deeper than mere hunting. It was a war of territorial displacement. As we laid down steel rails and built fences, we were not just claiming land, we were fragmenting the very concept of the hunt. For a wolf, survival depends on the ability to traverse vast, uninterrupted landscapes to follow the seasonal migrations of prey. By carving the world into fenced enclosures and human corridors, we triggered a phenomenon known as habitat fragmentation. We didn't just kill the wolves, we broke the machinery of their existence. We trapped them in islands of forest, isolated from the genetic diversity required to sustain a healthy population. This period also saw the weaponization of biology. The introduction of invasive species and the alteration of entire river systems changed the landscape of fear that wolves had helped maintain. As wolves vanished, the trophic cascade, the ripple effect of a predator's influence, began to fail. Without the wolf to regulate the herds, ungulate populations exploded, leading to overgrazing that stripped the land bare. We were inadvertently dismantling the very foundations of the ecosystems we sought to tame. By the mid-20th century, the wolf was on the brink of a biological collapse. In many parts of the world, they had been driven to near extinction, relegated to the most inhospitable corners of the globe. The top hunter had been hunted to the edge of the abyss. We had achieved our goal. The landscape was quiet, the livestock were safe, and the wild was being tamed. But in our pursuit of a world without shadows, we had created a profound ecological void, a silence in the woods that whispered of a missing piece in the engine of life. The predator was gone, but the consequences were only just beginning to take hold. What does a world look like when the heartbeat of the hunt stops? To the human eye of the early 20th century, the absence of the wolf looked like a victory. The forest seemed more peaceful, the herds seemed more abundant, and the livestock seemed more secure. But nature does not recognize the concept of peace as a lack of conflict, it recognizes balance. And when we removed the wolf, we didn't just remove a predator. We pulled the keystone from a living arch, and the entire structure began to groan under its own weight. This is the story of the ecological void, a period where the landscape of fear collapsed, and in its place, a landscape of unintended consequences emerged. In biology, there is a concept known as top-down regulation. For millennia, the wolf had acted as the invisible hand, a biological regulator that dictated the movements and numbers of every herbivore in its domain. When the wolves vanished, this regulation ceased. Without the constant, looming threat of a pursuit, large ungulate populations, deer, elk, and moose underwent a phenomenon known as ecological release. They were no longer the hunted, they became the masters of an unchecked domain. But this abundance was an illusion. Without the wolf to cull the old, the sick, and the weak, the herds did not just grow, they changed. They lost the evolutionary pressure to remain vigilant, and more importantly, they lost the necessity to keep moving. This triggered a devastating process of overgrazing. In many ecosystems, deer and elk began to congregate in sensitive riparian zones, the lush, green corridors along riverbanks and streams. Because there was no longer a landscape of fear, to drive them away from these vulnerable areas, they stayed. They grazed the young willow, aspen, and cottonwood shoots down to the nub before they could ever reach maturity. The results were catastrophic, and at the time, baffling to scientists. As the riparian vegetation vanished, so did the engineers of the river. Without the roots of young trees to stabilize the banks, erosion accelerated. Rivers began to widen, shallow out, and lose their complexity. The intricate pools and riffles that provided habitat for fish, amphibians, and aquatic insects began to silt up and disappear. The void extended even to the birds. As the willow thickets were stripped bare, the songbirds that relied on them for nesting material and protection found themselves homeless. The entire vertical architecture of the forest, from the soil to the canopy, began to flatten. We were witnessing a trophic meltdown, where the loss of a single apex predator caused a downward spiral of biodiversity. Even the scavengers, the opportunists of the wild, began to starve. In a healthy ecosystem, the wolf provides a consistent, year-round supply of carrion, the leftovers of a successful hunt. This pulse of protein supports everything from grizzly bears and wolverines to ravens and beetles. When the hunt stopped, the steady supply of carrion dried up. The scavengers were forced into more frequent, and often fatal, conflicts with humans as they searched for sustenance in our backyards. The silence we had fought so hard to achieve was not the silence of a balanced world. It was the silence of a dying one. We had removed the predator, thinking we were cleaning the house, only to realize we had accidentally broken the very clockwork that kept the house standing. But what happens when the clockwork begins to turn again, only to find the gears are no longer compatible with the machine? If the era of eradication was a period of silence, the modern era is one of friction. As we enter the 21st century, a small number of wolf populations have begun to reclaim their ancestral territories. But they are not returning to the vast, unbroken wilderness of their ancestors. Instead, they are returning to a world that has been fractured, partitioned, and paved. They are entering a landscape defined by the modern siege. For a predator that evolved to master the geometry of the chase and the vastness of the horizon, the modern world is a labyrinth of lethal obstacles. Consider the road. To a wolf, a highway is not merely a path of transit. It is a high-speed gauntlet of unpredictable kinetic energy. Research into wolf mortality suggests that vehicle strikes have become one of the leading non-natural causes of death for dispersing juveniles. For a young wolf, driven by the biological imperative to find new territory and establish a pack, a multi-lane interstate is a biological dead end. A sudden, violent disruption of the very gene flow required for the species' survival. Then there are the fences. The wolf's greatest evolutionary advantage is its ability to move across entire ecosystems to track the seasonal migrations of its prey. But the modern world is a patchwork of property lines. Wire fences, cattle guards, and impenetrable enclosures act as artificial barriers that fragment habitats. This fragmentation creates islands of wilderness, trapping packs in small pockets of land where they may eventually face genetic stagnation due to a lack of new bloodlines. And then there is the most intimate point of conflict: the livestock. As wolves reemerge into landscapes that humans have repurposed for agriculture, the ancient tension between predator and provider reignites. To a wolf, a sheep or a calf is not property. It is a high-calorie, low-risk biological opportunity. In an environment where natural prey like elk or bison may be scarce or heavily managed, the easy kill of a domestic animal becomes a survival necessity. This creates a phenomenon known as human-wildlife conflict, a psychological and economic siege. For the rancher, the wolf is a thief. For the wolf, the ranch is simply a new kind of territory. This conflict is often exacerbated by the edge effect, the biological reality that as human development encroaches on wild spaces, the interface where wolves and livestock meet becomes longer and more frequent. But the siege is not just physical, it is also sensory. The wolf's world is built on a foundation of hyperacute scent and sound. In the modern world, this foundation is under constant bombardment. The pervasive, acoustic fog of industrial noise and the chemical signatures of human expansion can mask the scent of prey or the warning calls of a rival pack. We are witnessing a profound evolutionary mismatch. The wolf is attempting to apply millions of years of specialized hunting intelligence to a world that no longer follows the rules of the wild. They are masters of a game where the board is constantly being rearranged. The boundaries are being drawn by hands they cannot see, and the very ground beneath them is increasingly made of asphalt and steel. The hunter has returned, but the hunt has become a siege. How do you rewrite a story that has been etched into the human psyche for 10,000 years? For millennia, the wolf was the shadow in the periphery of the campfire, the personification of chaos, and the ultimate antagonist in the human drama of progress. We didn't just fear them, we mythologize them. We turn them into monsters to justify our crusade to erase them. But as we stand in the wreckage of the ecosystems we dismantled, a quiet, scientific revolution is beginning to dismantle our myths. We are moving away from a narrative of pest control and toward an understanding of biological necessity. The shift began not with emotion, but with data. For decades, we viewed the wolf through the lens of a zero-sum game. More wolves meant less livestock. More wolves meant less safety. But the emergence of trophic cascade theory, the study of how top predators influence every level of an ecosystem, has flipped the script. We realized that when we removed the wolf, we didn't just remove a predator. We removed the architect of the landscape. Consider the green world hypothesis. In the absence of wolves, herbivore populations like elk and deer don't just grow, they become sedentary. Without the constant pressure of the hunt, they stop moving. They congregate in valleys and riverbeds, overgrazing the vegetation until the very soil loses its ability to hold water. The rivers change course, the birds lose their nesting sites, and the entire biological machinery begins to seize. The wolf is not a thief of life, but a regulator of it. This is the core of the keystone concept. Just as the keystone in a stone arch holds the entire structure against the force of gravity, the wolf holds the ecosystem against the force of collapse. When we look at the reintroduction of wolves in places like Yellowstone, we aren't just seeing the return of a carnivore. We are seeing the return of a biological pulse. We see willow trees recovering, which brings back beavers, which creates wetlands, which brings back fish and amphibians. This is the top-down control that keeps nature from spiraling into a monoculture of overgrazed wasteland. However, shifting our perception is more difficult than updating a textbook. It requires us to confront a psychological discomfort, the realization that the monster was actually a vital organ of the planet. Science has also begun to illuminate the complex, nonlinear ways wolves interact with their environment. We are learning about fear ecology, the idea that the mere presence of a wolf changes the behavior of every other animal. This landscape of fear is not a negative thing. It is a vital mechanism that prevents any single species from exhausting the resources of the land. It forces movement, it creates diversity, and it ensures that no single part of the machine burns out. We are learning to see the wolf not as an intruder in a human world, but as a necessary component of a functional one. The transition from monster to keystone is perhaps the greatest intellectual challenge of modern conservation. It requires us to stop seeing the world as a collection of resources to be managed and start seeing it as a complex, interconnected web where the hunter is just as essential as the hunted. The question is no longer whether the wolf can survive our world. The question is whether we can survive a world without them. What happens when you reintroduce a ghost into a world that has forgotten how to breathe? In 1995, the inhabitants of Yellowstone National Park were living in a biological stalemate. The ecosystem was a landscape of stagnation. Without their primary predator, the elk populations had become sedentary, bloated, and ecologically reckless. They had settled into the river valleys like a slow-moving tide, stripping the banks of willow, aspen, and cottonwood. The rivers were widening, eroding, and choking on their own silt because there was no one to force the herds to keep moving. The heartbeat of the park had slowed to a crawl. Then the wolves arrived. The reintroduction of the gray wolf into Yellowstone wasn't just a conservation project. It was a high-stakes biological experiment in trophic cascades. We often speak of the wolf's impact in terms of what they kill, but the true miracle lies in what they change through the mere shadow of their presence. As the wolves began to hunt, they didn't just reduce the number of elk, they fundamentally restructured the elk's psychology. This is the practical application of the landscape of fear we discussed earlier. The elk could no longer afford to linger in the open valleys or graze aimlessly in the riparian zones. They had to stay vigilant. They had to move. They had to stay on the move to avoid becoming a predictable target. And in that movement, the earth began to heal. With the elk forced out of the riverbeds, the vegetation underwent a miraculous resurgence. Willow and aspen, once stunted by decades of overgrazing, began to reach for the sky. This wasn't just a win for the trees, it was a domino effect of life. As the willow thickets grew, they provided the essential materials for beavers to return. The beavers, in turn, became the landscape's engineers, building dams that slowed the flow of water, created deep pools, and replenished the groundwater. These new wetlands became nurseries for amphibians, habitats for fish, and drinking holes for birds and insects. Even the scavengers felt the pulse return. The carcasses left behind by wolf kills became vital, year-round food sources for grizzly bears, bald eagles, and ravens, providing a predictable caloric windfall that stabilized their populations during lean seasons. But the miracle extends even deeper, into the very chemistry of the soil and the physics of the water. The increased vegetation stabilized the riverbanks, reducing erosion and causing the river channels to narrow and deepen, becoming more stable and complex. We saw a landscape that had been dying of stasis suddenly spring into a state of dynamic equilibrium. The Yellowstone case study proved that an apex predator is not a luxury, it is a functional necessity. It taught us that you cannot fix a broken system by simply managing the pieces. You have to restore the processes. You cannot manage a forest into health. You must allow the hunger of the hunter to drive the growth of the green. Yellowstone stands as a living testament to the fact that nature is not a collection of static parts, but a series of flowing connections. When you restore the predator, you don't just bring back a hunter, you jumpstart the engine of life itself. The wolf didn't just return to Yellowstone, the wolf made Yellowstone. If Yellowstone was the proof of concept, then the rest of the continent became the grand, sprawling laboratory. But how do you scale a miracle? How do you take a single, localized success and translate it into a continental strategy of rewilding? The science of bringing the hunter back is far more complex than simply opening a cage and letting a predator loose. It is a delicate dance of landscape ecology, genetic management, and spatial mathematics. To rewild a continent, scientists have to move beyond the species-centric model, which focuses only on the wolf, and adopt a process-centric model, which focuses on the restoration of entire ecological functions. One of the most critical, yet invisible, hurdles in this scientific endeavor is the connectivity problem. In the era of the wolf's eradication, humans didn't just kill the animals, we fragmented their world. We carved the continent into isolated islands of habitat, separated by a labyrinth of interstate highways, sprawling suburbs, and endless fences. For a wide-ranging carnivore like the wolf, a forest is not a home if it is surrounded by a sea of asphalt. To combat this, modern rewilding utilizes the science of corridor ecology. We are no longer just looking at where wolves live, but where they travel. By identifying and protecting migratory corridors, strips of habitat that allow for safe passage between larger wilderness areas, we allow for gene flow. Without these corridors, reintroduced populations become genetic islands, susceptible to inbreeding depression, which can weaken the very predatory instincts that make them successful. Scientists are now using satellite telemetry and GIS modeling to predict these invisible highways, attempting to stitch a fractured continent back together. Then there is the intricate science of metapopulation dynamics. A single, massive pack is a target. A network of smaller, interconnected populations is a resilient system. Rewilding experts must calculate the minimum viable population. The threshold of individuals required to ensure a species can survive environmental shocks, such as a disease outbreak or a particularly harsh winter. This isn't guesswork. It involves complex stochastic modeling to ensure that the new wolves aren't just a temporary visitor, but a permanent fixture. But perhaps the most challenging frontier is the social ecological feedback loop. Science tells us that the wolf needs the forest, but it also recognizes that the forest exists within a human-dominated landscape. True rewilding requires coexistence science, studying the behavioral responses of both the predator and the human neighbors. This involves developing non-lethal deterrents, such as fladry, colored flags that mimic predator boundaries, and livestock guardian animals, to minimize the friction between the hunter and the human. We are learning that rewilding is not an act of returning to a pristine past, but an act of engineering a functional future. It is the realization that the top hunter is a moving target in a changing climate. As we move forward, the goal is no longer just to count the number of wolves in a forest, but to measure the strength of the connections they restore. We are learning to design a world where the hunter is no longer a ghost, but a vital, breathing part of a continent that is finally learning how to be wild again. But what happens when the biological blueprint itself begins to fray? If corridors are the highways and metapopulations are the cities, then genetics is the very code that keeps the entire machine running. As we stitch the landscape back together, we face a silent, microscopic crisis: the erosion of the genome. In a continuous, prehistoric wilderness, wolves enjoyed a vast, effective population size, a mathematical term describing the number of individuals contributing genes to the next generation. This massive pool acted as a biological buffer, a reservoir of diversity that could absorb mutations and adapt to changing climates. But in our fragmented world, that reservoir is drying up. When a population is trapped in a genetic island, we witness the onset of inbreeding depression. This isn't just a theoretical concern, it is a physical reality that can dismantle a predator from the inside out. In isolated pockets, recessive deleterious alleles, genetic errors that are usually masked by healthy dominant genes, begin to pair up. This can manifest in reduced litter sizes, compromised immune systems, and even skeletal deformities that strip the wolf of its greatest asset, its physical endurance. If a wolf cannot run, it cannot hunt. If it cannot hunt, the lineage ends. However, the wolf is demonstrating a capacity for resilience that challenges our understanding of evolutionary speed. We are seeing the emergence of adaptive plasticity. In some fragmented regions, wolves are showing an uncanny ability to navigate anthropogenic landscapes, human-altered environments. Some populations are even exhibiting subtle shifts in their circadian rhythms, becoming more nocturnal to avoid human contact, a behavioral adaptation that may eventually be reinforced by genetic selection. But there is a deeper, more complex phenomenon at play: the genetic rescue effect. Scientists have discovered that even a tiny amount of new blood, the introduction of just a few unrelated individuals into an isolated population, can trigger a massive surge in fitness. This is the biological equivalent of a software patch, correcting errors and revitalizing the population's ability to survive environmental stressors. We are now seeing experimental efforts to facilitate assisted gene flow, where humans act as the surrogate for the missing corridors, physically moving individuals to prevent the genetic stagnation that fragmentation demands. Yet, we must also confront a more unsettling reality: the genetic homogenization trap. As we connect habitats and move wolves to prevent inbreeding, we run the risk of erasing the very local adaptations that make different wolf lineages unique. A wolf from the subarctic tundra is a biological masterpiece tuned to the cold. A wolf from the temperate forest is tuned to the shadows. If we create a single, massive, genetically uniform superpopulation, we might inadvertently strip the species of the specialized toolkits it needs to survive localized environmental shifts. The question of genetic resilience, then, is not just whether the wolf can survive the fences and the roads, but whether it can maintain the exquisite, specialized diversity that allowed it to become the world's top hunter in the first place. We are no longer just managing a species, we are managing an evolutionary trajectory. To ensure the wolf's future, we must ensure that its journey through the modern world is not just a movement through space, but a continuous, vibrant flow of life through time. How do you shadow a ghost that has spent millennia perfecting the art of being unseen? For most of human history, our understanding of the wolf was built on fragments: a footprint in the mud, a howl in the distance, or the carcass left behind. We were outsiders looking in, guessing at the rhythm of a life we could never truly touch. But in the modern era, the veil is being lifted. We are no longer merely observers of the hunt, we have become its silent, digital witnesses. To protect the wolf, we have had to learn to see as they see, to track not just their bodies, but their very essence through the data they leave behind. The cornerstone of this modern surveillance is the GPS collar, but to call it a simple tracking device is an understatement. These are sophisticated biologging laboratories strapped to the neck of a predator. Today's telemetry goes far beyond simple latitude and longitude. We are now utilizing triaxial accelerometers, sensors that measure the exact orientation and acceleration of a wolf's movement in 3 dimensions. This allows scientists to perform ethology from a distance. By analyzing the high-frequency data spikes in a wolf's movement, we can mathematically distinguish between a casual stroll, a social play session, and the high-intensity, rhythmic gait of a pursuit. We can literally watch a hunt unfold on a computer screen, identifying the exact moment a pack transitions from scouting to the strike, all without ever stepping foot into their territory. But the technology has moved even deeper into the very chemistry of the animal. In the past, monitoring a population meant capturing a wolf, drawing blood, and releasing it, a stressful and intrusive process. Now, we are entering the age of non-invasive genomics. Through the use of scat detection dogs, highly trained canines capable of locating microscopic biological samples across vast landscapes, we can collect DNA without ever touching the predator. This allows us to map the genomic landscape of a territory. We can identify individual wolves, determine their sex, and even calculate their kinship coefficients simply from a piece of waste left on the forest floor. We are building a digital census of a species that has spent an eternity avoiding the human eye. Even more profound is the integration of remote sensing and AI. We are now deploying camera trap arrays that utilize machine learning algorithms to sift through millions of images, instantly identifying specific individuals by their unique coat patterns or scarring. When combined with satellite imagery that tracks changes in vegetation and prey density, we can create predictive models of predation. We are learning to map the landscape of fear, not just where the wolves are, but where they will be based on the intersection of topography, moonlight, and prey migration. This is a strange, new symbiosis. We are using the pinnacle of human technological achievement to peer into the most primal of biological processes. We are using silicon and satellite signals to decode the ancient, instinctual language of the pack. Yet, as we wrap the world in this digital web, a fundamental question remains. In our quest to monitor every heartbeat and every kill, are we truly understanding the wolf, or are we simply turning the wild into a laboratory? We are gaining unprecedented clarity, but the true mystery of the hunter remains, a shadow that even the most advanced sensor can only hope to touch. But as the digital veil thins, a new and more volatile conflict emerges, not one of biology or technology, but of values. If the GPS collar provides us with the where and the DNA provides us with the who, we are still left grappling with the should. We have successfully mapped the ghost, but now we must decide how to live with it. This is the ethical frontier, the collision between the scientific necessity of the wolf and the socioeconomic realities of the humans who share its territory. The debate is often framed as a binary struggle: conservationists versus ranchers, or urbanites versus rural dwellers. But the reality is a complex web of human-wildlife conflict that defies simple categorization. At the heart of this tension is the concept of compensatory mortality. In many management models, when a wolf predates on livestock, the state provides financial compensation to the rancher. However, biologists argue that this is a superficial fix. It addresses the economic loss, but it fails to account for the behavioral cascades in prey. When wolves are present, livestock and wild ungulates don't just face the threat of death, they face the threat of constant, high-stress vigilance. This non-lethal cost, increased cortisol levels in cattle, reduced grazing efficiency, and altered movement patterns, can degrade the health of a herd just as effectively as a direct kill. Furthermore, we are facing a crisis of spatial mismatch. As human infrastructure, highways, fences, and sprawling suburbs fragments the landscape, we are inadvertently forcing the wolf into closer proximity to human life. We are creating ecological traps, where the very habitats we have designated for wolf protection are actually corridors of high mortality, where wolves are frequently struck by vehicles or encounter domestic dogs carrying pathogens like canine distemper or parvovirus. This brings us to the most contentious tool in the management toolkit: the lethal removal versus non-lethal deterrent debate. Proponents of management argue that to maintain social license for wolf presence, we must allow for the removal of problem individuals, wolves that show a learned preference for livestock. They argue that a predator that adapts to human resources is no longer a wild actor, but a management liability. Yet the opposition points to a terrifying biological reality: the social destabilization effect. In many species, removing an alpha or a dominant breeder doesn't just reduce the population, it shatters the pack's social architecture. When a pack's hierarchy is broken by a management cull, the resulting social vacuum can lead to increased wandering, more frequent territory disputes, and a paradoxical increase in livestock depredation as younger, less experienced wolves attempt to establish themselves. We may be trying to solve a problem through removal, only to trigger a chaotic surge in the very behavior we seek to suppress. As we stand on this frontier, we are forced to ask: is management an act of stewardship, or is it an attempt to domesticate the wild through data and dosage? Are we creating a sustainable coexistence, or are we merely designing a highly controlled, artificial version of the wild? We have mastered the art of tracking the hunter. Now, we must master the much harder art of sharing the world with it. What if the true measure of a species isn't how long it survives, but how deeply it defines the very world it inhabits? To understand the wolf is to understand that they are not merely inhabitants of the ecosystem, they are its architects. We have spent centuries viewing them through the lens of conflict, as a problem to be managed, a ghost to be tracked, or a monster to be feared. But as we move beyond the data points and the heated debates of management, we arrive at a more profound realization. The wolf is a fundamental constant in the grammar of life on Earth. The legacy of the wolf is written in the very geometry of the landscape. We see it in the trophic cascades that have revitalized entire river systems, where the presence of a predator dictates the path of a stream by controlling the grazing patterns of elk. We see it in the landscape of fear, a subtle, invisible pressure that forces every living thing to remain sharp, to remain vigilant, and to remain part of the evolutionary dance. Without the wolf, the world doesn't just lose a predator, it loses its tension. It becomes a world of stagnation, where the lack of selective pressure leads to a biological thinning of the herd. But their legacy is even more intricate than the visible changes in flora and fauna. There is a deep, evolutionary memory embedded in the wild. scientists have begun to explore the concept of niche construction, where certain apex predators don't just occupy a space, but actively shape the evolutionary trajectory of their prey. The wolf has been a silent partner in the refinement of the ungulate, a biological sculptor that has, over millennia, honed the speed, the stamina, and the sensory acuity of the deer, the elk, and the bison. In a sense, the wolf is the invisible hand that has polished the wildness of the world. Even as we attempt to fence them in or study them from a distance, the wolf remains an outlier in the Anthropocene. While most of the world's megafauna have been relegated to zoos or managed preserves, the wolf maintains a terrifying and beautiful autonomy. They possess a behavioral plasticity that is almost unparalleled, the ability to shift from hunting elk in the frozen tundra to navigating the fragmented edges of a suburban forest. This resilience suggests that the wolf is not a relic of a bygone era, but a highly sophisticated survival machine capable of navigating the chaos of the modern age. As we close this chapter of our journey, we must look past the scars of history and the complexities of modern coexistence. We must recognize that the wolf represents something primal that humanity is only beginning to rediscover: the necessity of the untamed. The wolf is the shadow that gives the light its meaning. They are the reminder that the world is not a garden to be manicured, but a complex, breathing system of checks and balances. Their legacy is not found in the numbers on a census or the maps of a conservation zone, but in the very heartbeat of the wilderness itself. As long as there is a predator to challenge the prey, as long as there is a chase that tests the limits of endurance, the wolf will remain the eternal hunter, the architect of the wild, and the enduring pulse of the natural world.